Hi, my name is Natalie Hayes, and my project is solving for the gravitational acceleration by finding the viscosity of honey using different sized spheres. My research question is finding the viscosity of honey using different sized spheres and Stokes' law. What is the acceleration of gravity? My hypothesis is that the spheres with a larger mass will have a larger terminal velocity due to a stronger force of gravity being exerted on it. Contrarily, spheres with a smaller mass will have a smaller terminal velocity because a weaker force of gravity will be exerted on it. The purpose of this is to see if testing the viscosity through the equation derived from the three forces acting upon a sphere falling through a field of liquid will be sufficient in solving for the acceleration of gravity. An object in a fluid field experiences frictional force opposite to the direction of motion. The measure of this frictional force is given by the dynamic viscosity of the object. Stokes' law was derived for the frictional force, also called the drag force, exerted on spherical objects with a very small Reynolds number in a viscous fluid. When the sphere is falling through the fluid in an infinite field, it is assumed that once the sphere reached a terminal velocity and equilibrium is achieved, all forces acting upon the sphere will balance out. The three forces acting upon the sphere are Stokes' law, the force of buoyancy, and the drag force. The equation is viscosity equals 2/9 radius squared times the density of the sphere minus the density of the fluid times gravity over velocity. The independent variable is the size of the spheres, the dependent variable is the velocity of the spheres, and constants are the type of honey I'm using, the amount of honey, and the temperature of the room throughout the experiment. My materials are a graduated glass cylinder filled with honey, seen at the picture on the right, steel spheres and a veneer caliper, seen on the bottom picture, a stopwatch, a conical flask, a digital balance scale, seen on the top picture, and 100 milliliters of honey. My procedure is to measure and record the mass of each sphere using the digital scale, to record the diameter of each sphere using a veneer caliper, and the mass of the graduated cylinder without honey. Next, I will measure and record the height of AB and BC, then pour 100 milliliters of honey into the cylinder and record its mass. I will calculate the mass of the honey itself by subtracting the cylinder with honey from the cylinder without honey. Next, I will calculate the volume of the honey, and then I will calculate the volume of each sphere using the equation volume equals 4/3 pi r cubed. Then the density of the honey using the equation density equals mass over volume. Next, I will perform my trials by dropping each sphere into the honey and repeating this step for each variable. My collected data for each sphere was the mass and diameter. Then with these variables, I could calculate the volume and the density. The density collected for each sphere was within the accepted range of densities for the steel of the balls that I was using, with the variation being errors in mass and diameter collected data calculations. Each sphere was dropped into the honey 3 times, and velocity was calculated through the equation velocity equals distance over time. Distance of AB and BC were both 0.0515 meters. Average velocity was found from AB and BC averages for each sphere. Viscosity was found by plugging all variables collected and calculated into the viscosity equation. In order to solve for the acceleration of gravity of each sphere, the viscosity equation was arranged to solve for gravity, as seen below. Linearized data is as seen here. X values were attained from the denominator of the equation, and the y values were attained from the numerator, equating to rise over run and the slope. In effect, the slope of the graph equaled 10.55, as the accepted value of gravity is 9.8 meters per second squared. The graph is a linear function and it has a slope of 10.55 meters per second squared. The slope is positive because the spheres are accelerating at the rate of gravity. The slope represents the acceleration of gravity. After graphing my data, the slope was determined to be 10.55, which was the final value for the acceleration of gravity that I derived for this experiment. Considering that the accepted value of gravity is 9.81 meters per second, my value is relatively close. I found only a 7.65% difference using the percent error equation. The errors in my experiment were that it was a non-infinite fluid field, so the sides of the tube could have interfered with the sphere's velocity. There could have been systematic errors in the vernier caliper and the scale measurements, and when I was recording the time, parallax error could have occurred, based on when I chose to start and stop the ball as it fell past each checkpoint. Mirroring of an infinite fluid using equidistant points AB equals BC in order to make sure the sphere was falling near the accepted value of gravity before recording my times. Viscosity as a function of temperature. Viscosity of the same liquid can vary at different temperatures, so I kept the room at the same temperature throughout the experiment. The purpose of the experiment was to determine if the viscosity of honey could be solved for by using Stokes' law, and thus gravity. As viscosity and velocity were inversely proportional, when the mass of each sphere increased, the terminal velocity increased, and therefore the viscosity went down. The accepted range for the viscosity of honey is between 2.4 and 23.4 pascals at 25 degrees Celsius. This value range tells me that my range of values for my specific honey used was valid, as my density for this honey was higher than normal honey density, about 400 kilograms per meters cubed, and thus my viscosity was above range.